The operation begins with an airframe buried under decades of structural overprint. The target is a consolidated B-24A Liberator. This specific aircraft is the 25th airframe off the assembly line. Out of a total production run exceeding 18,482 units, this is the oldest survivor. Contracted in 1940 and completed for British acceptance in May 1941, it carried the administrative designation AM-927. The objective is precise. An engineering team must reverse engineer decades of civilian transport modifications. The goal is to rebuild the extinct B-24A bomber configuration and restore the primary load paths of a 1940 heavy bomber. The stake is operational survival. If the baseline geometry cannot be mapped and restored under modern airworthiness standards, the aircraft remains grounded. That baseline was complicated by ownership history and decades of civilian service. When Petróleos Mexicanos loaned the aircraft to the Commemorative Air Force in 1967, before full ownership passed in May 1968, the airframe lacked its original military identity. Following an early loss of combat utility, the aircraft had been permanently converted into a transport, and decades of executive service physically overprinted the military structure. Civilian passenger windows cut into the fuselage skin, while plush interiors and cargo modifications altered the internal volume and concealed the original bomber load paths. Removing it became a controlled structural disassembly centered on the wing roots, fuselage bulkheads, and surviving primary structure. The forensic gap came down to a part-by-part audit, including which rivets held 1940 factory aluminum and which held later executive retrofits. Those cuts also broke the continuous fuselage shear webs, so replacement skins had to recreate the original stress distribution for combat loads. Removing the plush interior exposed altered bulkheads and relocated control runs. The team faced a complex material preservation problem. They had to document the location of every missing bomber component. They had to evaluate the fatigue life of the surviving metal under the civilian floorboards. The engineering team had to document the routing of every modern electrical wire and hydraulic line installed by the corporate operator. These secondary systems often routed directly through spaces originally designed for military hardware. Rerouting them without violating modern flight safety rules added strict procedural limits to the preservation effort. The team could not simply rip out the civilian systems, they had to engineer replacement paths that honored the 1940 structural limitations. Because the aircraft was the 25th airframe, its 1940 construction predated wartime standardization and preserved early configurations absent from later models. This lack of standardized documentation forced the team to rely on direct physical evidence rather than generalized blueprints. The team removed the interior paneling systematically, cataloging internal rivet lines, frame stations, and skin evidence around the transport window cutouts. Each cutout represented a localized weakening of the fuselage skin tension. The reversion required fabricating continuous aluminum sheets to replace the windowed sections. The newly riveted skins had to restore the original structural tension required for flight stability. The recovery team operated in a cold zone environment. The aircraft rested on the hangar floor, where environmental weathering and metal fatigue were the primary hazards. Corporate transport maintenance had replaced early military hardware with commercially available parts, so the baseline configuration had to be proven before any new metal could be cut. The team slowly excavated the bomber geometry from beneath the civilian overprint. The transport modifications were mapped and scheduled for removal. The core structure remained intact despite the heavy alterations. The forensic mapping answered how the aircraft survived as a civilian asset. It did not answer why the airframe was stripped of its military role in the first place. The original combat configuration was not lost to combat but to an early operational failure. What specific force vector shattered the military trajectory of the aircraft and forced its initial abandonment? The geometry of the 67-foot airframe created a severe mechanical vulnerability during runway operations. In 1941, the aircraft was associated with the projected U.S. Army Serial 40-2366, but its operational identity was the British serial AM-927. It was conducting a routine training flight in Albuquerque, New Mexico. The aircraft touched down and began its normal deceleration phase. During the landing rollout, a localized mechanical failure permanently altered the operational environment of the aircraft. The right main wheel brake locked or turned too slowly against the landing roll. The aircraft departed the runway, the right main gear collapsed, and the nose gear failed in the sequence that followed. The tricycle landing gear configuration was a relatively modern design for heavy bombers at that time, offering superior ground handling under normal conditions, but possessing specific structural vulnerabilities. When the right main wheel brake locked, it created immediate asymmetrical braking force. The drag pulled the aircraft off its landing path and overloaded the landing gear sequence. The confirmed damage record is severe enough without inventing an unseen fracture path. The failure drove the forward fuselage into the runway surface. The engineering assessment recorded structural displacement that reached beyond the nose into the lower forward fuselage and the primary bomb bay sections. The damage to the lower bulkheads, the bomb bay frames, and the longitudinal stringers was extensive, restoring the bomber geometry, including the bomb bay doors, defensive stations, and internal munitions bracing, would have demanded factory-level remanufacturing beyond the training program's time, material, and engineering limits. This mechanical failure forced a permanent operational shift. The physical damage crossed an irreversible procedural threshold. The British ministry, the original contracted operator, and the manufacturer reached a formal, institutional agreement to completely abandon the military future of the airframe. The damage was simply too severe for any reasonable combat delivery schedule. Instead of scrapping the relatively new aircraft, engineers and administrators made a calculated trade-off decision. They permanently struck the airframe from combat rosters and elected to convert it into a dedicated transport aircraft. The damaged bomb bays were permanently sealed rather than rebuilt. The complex military bulkheads were not repaired according to the original 1940 bomber blueprints. They were instead structurally simplified and heavily reinforced to support internal cargo floorboards and passenger loads. The conversion from bomber to transport required specific structural compromises. The engineers removed the provisions for forward defensive armaments because the supporting forward structure was compromised. They riveted heavier continuous skin panels over the lower fuselage where the bomb doors previously operated. This action added localized weight but restored the aerodynamic integrity of the lower hull. The repair crews focused on airworthiness for logistical transport, allowing cargo capacity and repair turnaround to drive the structural choices. By sealing the damaged lower sections and installing continuous transport flooring, the 1941 repair crews fundamentally altered the structural load paths of the aircraft. The airframe survived the Albuquerque accident, but it emerged with an entirely different operational purpose. The wartime timeline favored a fast, utilitarian conversion over factory-level bomber reconstruction. The aircraft would fly for decades under this altered structural reality. With the bomber destroyed as a combat asset, how would engineers map its extinct configuration 60 years later? The engineering team faced a visible physical contradiction on the hangar floor. In 2006, that restoration entered its visible structural phase, including the removal of civilian windows and the reconstruction of bomber gun positions. However, the airframe still operated with PBY Catalina engine cowlings. These distinctive flying boat cowlings were left over from its experimental transport era. They altered the aerodynamic and thermal profile compared to original military supercharger cowlings. This hardware mismatch defined the forensic problem. Engineers now had to decide which inherited components could remain under modern operating constraints. Proving the early military identity required isolating the original 1940 load paths from a web of later mechanical substitutions. To verify the extinct configuration, the team matched the physical dimensions of the fuselage against historical archival documents. The defining evidence began in the forward fuselage, but the aircraft no longer carried a pure early short nose. The team verified the AM927 serial history against surviving early B-24A evidence while accounting for the longer nose added during its later transport and development life. That surviving contradiction became part of the proof, separating the original early bomber identity from the later physical substitutions layered over it. They stripped out the remaining civilian passenger windows, mapped the internal aluminum bulkheads, and logged the exposed frame stations before replacement structure was approved. Precise fabrication came next. They fabricated obsolete 50 caliber replica gun installations for the nose, the waist, the belly, and the tail sections. Rebuilding these positions meant cutting back into the continuous aluminum skins that transport crews had previously installed over the openings. Engineers had to reinstall specialized bracing and structural webs to carry the load of the weapons. Those installations added localized mass to the extreme ends of the airframe. The fabrication process was strictly procedural. The team could not simply bolt weight onto the frame. They had to recalculate the structural tension across the entire 67-foot span to ensure the newly cut openings did not compromise the bending stiffness of the fuselage under dynamic flight loads. Adding mass to the extremities of the fuselage triggered a severe aerodynamic constraint inherent to the early bomber design. The short nose imposed a highly restricted longitudinal center of gravity envelope. The short nose limits forward mass leverage, making the airframe extremely sensitive to weight distribution changes. The center of gravity window on this specific aircraft is restricted to 11 inches. Adding weight outside that narrow longitudinal envelope shifts the center of gravity, not the center of lift, and can push the aircraft outside its approved stability margins. On the ground, the same sensitivity can increase the risk of a tail-heavy attitude if loading is handled carelessly. Every piece of fabricated aluminum and every replica gun mount had to be weighed and mapped against this severe mechanical limit. The engineering team operated within a zero-sum structural puzzle. When they removed heavy cargo decking from the center fuselage, the balance shifted. When they added 50 caliber replica gun installations at the tail, the balance shifted again. The retention of the PBY Catalina engine cowlings factored into these complex mass distribution calculations. The team constantly adjusted the internal ballast and structural layout to keep the aircraft safely inside the 11-inch parameter. The reversion successfully backdated the aircraft toward its early B-24A/RLB-30 appearance while maintaining the required longitudinal stability for safe flight operations. The fuselage again carried much of the early bomber's visual language. The internal evidence supported its identity, even though later substitutions, including the longer nose and later canopy structure, remained part of the flying artifact. Mapping the internal structure secured the aircraft's identity. The forward canopy became the next certification problem. The engineering team faced a strict procedural choice at the forward fuselage. A 1940 greenhouse canopy had to look credible from the outside, but the aircraft still had to meet operating limitations, inspection standards, and practical crew visibility needs. A structurally exact vintage canopy would add complexity, cost, and uncertainty. An undisguised later windshield would break the early war profile. The challenge was airworthiness fabrication, not cosmetic nostalgia. The original early bomber canopy was a complex, multi-paned greenhouse structure. It featured numerous intersecting aluminum frames supporting small, flat, transparent panels. Replicating this exact internal load path with modern materials presented a severe certification hurdle. The numerous joints and fasteners required by the original 1940 design created hundreds of potential failure points under the aerodynamic pressure of modern civilian flight profiles. Furthermore, the heavy framing restricted pilot visibility. While acceptable in early combat doctrine, this restricted field of view conflicts heavily with modern collision avoidance regulations. The team selected a calculated trade-off. They decided to construct a structural illusion. The engineers utilized a late-war, knife-edge windshield configuration as the primary structural foundation. This later canopy design possessed established airworthiness documentation and provided superior, uninterrupted sightlines for the flight crew. It utilized larger, stronger panels that easily met the modern impact and pressure requirements mandated by the aviation authorities. Engineers then bonded older-looking aluminum strips directly over the late-war canopy. These aluminum strips were non-structural. They were carefully bonded to the exterior of the continuous transparent panels to simulate the heavy, multi-paned greenhouse framing of the early bomber. Inside, the crew used the certified continuous windscreen. Outside, the added strips gave observers the early airframe silhouette. This process became the method fingerprint of the recovery, a cosmetic backdate built from period photo dimensions, while the late canopy remained the certified flying structure. The canopy compromise preserved the early war silhouette without surrendering the certification baseline. The next test came during a landing. A strict 14-month custom fabrication timeline defined the operational boundary following a sudden mechanical collapse. In May 2012, the aircraft was operating in Charlotte, North Carolina. During a routine landing sequence, the flight crew initiated the standard gear extension protocol. A high-pressure hydraulic line burst deep within the forward fuselage. With pressure loss, the system no longer had the mechanical advantage to drive and lock the heavy strut against gravity and slipstream. When the nose wheel contacted the runway surface, the unlocked strut immediately folded backward under the weight of the decelerating airframe. The forward fuselage dropped and scraped along the concrete. The damage was isolated but structurally critical. The impact crushed the lower nose skins and bent the main structural components of the nose gear assembly. The sudden collapse on an active runway created an immediate logistical hazard. Airport authorities needed the bomber cleared without adding damage to the irreplaceable forward fuselage. The confirmed record supports a narrower account. Temporary repairs followed the nose gear collapse, and the aircraft was later flown back to Addison, Texas, where the permanent repair effort began. Without a detailed recovery report, the event is best treated as emergency maintenance and repositioning, not as a documented sling and cradle salvage operation. The repair assessment revealed the central supply problem. As a unique surviving variant, the aircraft had no normal parts pipeline for the obsolete damaged components. The engineering team had to transition from flight operations into specialized repair and manufacturing, fabricating many replacement parts before the restoration could be completed in July 2013. The available record does not support a detailed reconstruction of hose type, routing path, or pressure margins. The safer statement is that the hydraulic system was repaired, inspected, and returned to service within the aircraft's operating limitations. The installation process was methodical. The machined parts were mated to the forward fuselage, and the modern hydraulic lines were connected, bled of trapped air, and pressurized. Drop tests confirmed the mechanical locks engaged correctly. The long grounding period ended when the reconstructed nose gear securely held the weight of the forward airframe. The next preservation problem moved from landing gear to the aging wing spars. A weight-dependent, never-exceed speed dictates the modern operational boundary of the 80-year-old airframe. FAA exemption material lists N24927 with a VNE of 305 knots at 41,000 pounds and 235 knots at 56,000 pounds. The engineering team enforces these administrative restrictions because the original military speeds, though higher in some configurations, would consume structural life too quickly on the modern airframe. By tying maximum allowed airspeed to operating weight, the team reduces peak aerodynamic stress exerted on the wing root spars. The speed restriction is paired with a strict mass limitation, a maximum operating weight of 56,000 pounds, significantly below the heavy bomb load takeoff weights of the early 1940s. Before every flight, crews calculate fuel against passenger and equipment weight to remain below that ceiling. Together, those limits reduce the bending moment on the center wing section during turbulence or maneuvering, and keep the 1940 aluminum alloys below cumulative cyclic stress limits. Outside the load path problem, the open hangar and flight line environment subjects the exterior to ultraviolet radiation, atmospheric moisture, and temperature cycling. While the thick aluminum hull resists these elements relatively well, the trailing edge flight control surfaces present a severe material vulnerability. The ailerons, the massive rudders, and the elevators of this early heavy bomber rely on a traditional dope and fabric covering over an internal metal skeleton. Over time, the environment systematically degrades the chemical integrity of the fabric and the tension holding it rigid. In 2024, inspection turned that environmental risk into a grounding decision. The cloth control surfaces were below safe margins, fabric tautness was degrading, and tail section control cables showed unacceptable wear. Loss of aerodynamic tension threatened flutter, a high-frequency vibration capable of tearing a control surface from its hinges. The available record supports an extended conservation intervention, but not a precisely documented 30-month interval. The maintenance crews removed the massive control surfaces from the tail empennage and the wings. Stripping the old material exposed the internal ribs and trailing edge spars, allowing direct visual inspection for hidden corrosion. Mechanics cleaned the metal framework, applied modern aviation corrosion protection, and verified the integrity of the hinges. They installed new primary flight control cables, routing them through the internal pulley systems that connect the cockpit yokes to the remote surfaces. The recovering process required precise physical discipline. Technicians stretched aerospace-grade fabric over the ribs, stitched it to the frames, shrank it to aerodynamic tension, and sealed the surfaces against weathering and ultraviolet exposure. The work restored the control surface profile without adding excessive weight at the margins. Together, these interventions define the aircraft's modern existence. The 25th airframe still flies only inside speed limits, weight control, exposure management, and constant attention to fabric tension. Its survival is not a return to 1940, but a managed flying condition that keeps one early Liberator visible in the air.